In this theorem, we are going to look at Gauss's theorem, where we relate divergence over a volume to flux through a surface. This is our overview slide, which we'll spend about 5 minutes going over before we go through each topic in more detail and with more examples. We start with Gauss's theorem given to us by this formula here, and it tells us that the volume integral of the divergence of a vector field A is equal to the surface integral of the field A. And this surface in particular is the surface that encloses this volume. And so what this tells us is the divergence over the volume is equal to the flux through the surface. And here, just to point out, we have a triple integral here on the left-hand side, and it's a triple integral over a volume of the divergence of A. And here we have the surface integral of A, where the surface, again, is the boundary of our volume. There will be a couple of things we need to review. First, I'm just going to review quickly the steps to take a surface integral on a vector field using the dot product. There are 4 steps. The first is to parameterize your surface and determine its domain. The second is to write our vector field in terms of the parameterization. The next is to calculate the unit normal, and then we plug in to this integral formula here. Since this surface integral is this the right-hand side of the Gauss theorem, we're going to do this quite a few times. The next thing we want to review is the Jacobian. And we use the Jacobian when we do a change of coordinate systems, which is quite frequent because often we have a vector field in rectangular Cartesian coordinates, but our surfaces or our volumes are cylinders or spheres. And so it's quite natural to want to change coordinate systems. Well, the Jacobian then tells us or gives us sort of a measure of how our change of coordinate systems will affect our surfaces. So for polar coordinates and cylindrical coordinates, the Jacobian is r, and for spherical, we'll be using rho squared sine of theta. Finally, we'll be doing a couple of examples where we calculate the volume of the divergence, and then we'll do a second calculation of the flux through the surface and see that they are equal. This is one of the examples we do here where we have a vector field and we have a surface of the cylinder. So we calculate the divergence of the vector field over the volume, which is this triple integral. And then we do a calculation of the surface integral of F, the flux. And we see that we get the same answer. We'll do this also for, let's see, this is a cylinder. We'll do this for a cube. And then we'll have a couple of other examples, including our last example, which is really convenient. It shows you when Gauss's theorem is super useful. So hopefully you can hang on until then. We'll start with our definition of Gauss's theorem, which actually we kind of covered pretty well. The idea is that if you have a volume integral of the divergence of a vector field A, that will equal to the surface integral of that vector field A, when the surface that we're integrating over is the boundary of the volume. So in other words, if our volume is an entire sphere, the interior of a sphere or a ball, let's think of a basketball, or actually I like a soap bubble. So the whole soap bubble, including the interior, is our volume, and then our surface is just going to be the soapy film on the outside that defines the volume. And on this side of the equation, on the left-hand side of Gauss's theorem, we have a triple integral over a volume, and we have the div of A, the divergence. And on the right-hand side, we have a surface integral, so that's going to be a two-dimensional integral or a double integral, and the surface again is the boundary of the volume. Without these physical interpretations, Gauss's theorem is pretty interesting because you're talking about knowing something about the interior of a volume just by looking at the surface. And if you add these physical descriptions, this Gauss's theorem also becomes more meaningful because you're saying something about the volume, the divergence of the volume, how things are spreading or expanding. You can determine that by looking to see how things are changing at the surface. Since we'll be doing these surface integrals, we want to review really quickly the steps to take a surface integral over a vector field using the dot product, and this was a topic of one of our previous videos. The first thing is we parameterize our surface and determine its domain. Remember, we think of a surface as being something from a two-dimensional domain that gets mapped into a three-dimensional space. And then we write our vector field then in terms of our parameterization of our surface. And if you recall, that's because our vector field is defined over the whole three-dimensional space, but we're only concerned about the vector field over the surface. So we compose V with our parameterization. Next, we calculate our normal to the surface, and the normal is defined as the tangent vector with respect to u crossed with the tangent vector with respect to v. So we take our parameterization, we take the partial derivative with respect to our first variable in our parameterization, that's tu, and we take our partial derivative with respect to our second variable of our parameterization, we cross them, we get the normal. And then last we plug into this formula. So when we have this integral, surface integral operation acting on a vector field with the dot product, that's equal to a double integral over our domain, du dv, our vector field composed of our parameterization dotted with our vector normal. And again, we're going to do an example of this like right away, like right now. Well, I lied. Maybe we're going to look at the Jacobian first. As I had mentioned, the Jacobian is used when you change from one coordinate system to another, and it represents the transformation of one unit volume in one coordinate system to another. And in polar coordinates and also in cylindrical, our Jacobian is r. In spherical, it's equal to rho squared sine of theta. And in case you want to transform to other coordinate systems, or you just want to be able to quickly calculate, say, the polar coordinates Jacobian and not memorize it, the Jacobian is this determinant matrix where if you're going from xyz to the uvw coordinate system, you take the partial derivative of x with respect to uvw, then you take the partial derivative of y with respect to uvw, and then you take the partial derivative of z with respect to u, v, and w. So we'll work this out for spherical and for cylindrical coordinates just so you can get used to this formula. We'll start with spherical coordinates. So x equals rho cosine theta sine phi, y is equal to rho sine theta sine phi, and z is equal to rho cosine phi. So the Jacobian, we're transforming x, y, z. In this case, u is equal to rho, v is equal to theta, and w is equal to phi. So the Jacobian is equal to our first coordinate, that would be the x coordinate, and then partial derivatives with respect to our u, v, w. In this case, it would be rho, theta, and sine. So x, partial derivative with respect to rho, is just cosine theta sine theta. Partial derivative with respect to theta is minus rho. Our cosine becomes a sine theta, our sine phi stays, and then partial derivative with respect to phi, we have a rho cosine theta, and then our sine phi becomes cosine phi. Next, we go to the y. For the second row, we go to the second coordinate, and we take the partial derivative, again with respect to rho, sine, and theta, and we'll get sine theta sine phi. Partial derivative with respect to theta, we'll get rho cosine theta, this will stay sine phi, and then partial derivative with respect to phi, we get rho sine theta, and the sine phi will become cosine phi. Finally, we take our last coordinate z, take partial derivative with respect to rho, theta, and phi. So partial derivative with respect to rho is cosine theta, partial derivative with respect to theta is 0, and partial with respect to phi is minus phi sine theta. And if we calculate this determinant, we are going to get negative rho squared sine phi, but for Jacobians, I should put a sign. No, maybe not. Yeah. For Jacobian, we use the positive version of it. So this will be rho squared sine phi because we want the positive orientation. I went ahead and did the determinant of this. So I started with in the I direction, we take this and we multiply by the determinant of the 2 by 2 matrix left. So I have cosine theta sine phi, and then the determinant of these two. So I have minus rho squared cosine sine squared phi. Here I get 0. Next, I'm going to have my minus rho sine theta sine phi. Where am I on here? Over here. Oh, except I also have to I have to alternate the sign, so that's plus sine theta sine phi, and then I take the cross product here, sine theta sine squared phi with a rho, a minus rho. Here, I'm going to get a rho sine theta cosine squared phi. Finally, I have my rho cosine theta cosine phi times the cross product of this 2 by 2 matrix, so that's a 0, and then I have my rho cosine theta cosine phi and sine phi. I do some calculations here, some algebraic manipulations or trig manipulations, and I finally get minus rho squared sine phi. So the Jacobian, as I said, to get the positive orientation, we take the positive rho squared sine phi. And one thing I'm going to say, this doesn't look that hard, but I feel like it's very easy to make a mistake. So when I'm in an exam, I don't really like to calculate this. I like to memorize this. For polar coordinates, it's not very difficult. You have x equals r cosine theta y equals r sine theta. When you take the Jacobian, it's the determinant of x. Partial derivative with respect to r is cosine theta. Partial derivative with respect to theta is minus r sine theta. For y, partial derivative with respect to r is sine theta, partial derivative with respect to theta is r cosine theta. Doing the determinant, cross multiplying, you get r cosine squared plus r sine squared, that just equals r. This, I probably wouldn't necessarily memorize, except after a while you remember it anyway, but this one's easy enough to calculate. Okay, now that we've kind of done a quick review of things, we can do this first example. Our first example problem is, let's say we have a vector field F, which is equal to xy squared y, and y. And let's say we have a surface S, and it's the surface of the cylinder x squared plus y squared equals 1. And it's bounded by the plane z equals 1 and z equals negative 1. And it includes the portions, the bottom surface of the cylinder, x squared plus y squared is less than or equal to 1 when z equals negative 1 and z equals 1. We want to verify Gauss's theorem. And to verify Gauss's theorem, we are going to have to calculate this two ways. First, we're going to calculate the divergence over a volume, and then the next thing we're going to do is calculate the flux over the surface. As we take our volume integral, we're going to take it of the divergence of F. So here I have my calculation of divergence, which is the del operator dotted with F, which is xy squared, x squared y, and y. So when we do the dot product, we have the partial derivative with respect to x, which will give us y squared, partial derivative with respect to y, which gives us x squared, and the partial derivative with respect to z, which gives us 0. And one thing I like to do so that later when I'm doing my volume integral, I don't accidentally use my f, but I actually want to use my div, I circle it over so that later I won't forget. The next thing we'll do is parameterize the volume of our cylinder. Using cylindrical coordinates, we have r cosine theta, r sine theta, and z, where r goes between 0 and 1 because we're given that it's a cylinder of radius 1. Theta goes between 0 and 2 pi, and z goes between negative 1 and 1 because we are given how the height, or the start and the bottom and the top of our cylinder. And one thing I'm going to mention now, what makes this a volume is the fact that we let r go from the center of the cylinder all the way out to the surface of the cylinder. If we wanted a surface, we would just set the radius equal to the radius of the cylinder, which is equal to 1. So instead of having r cosine theta, we would just have 1 cosine theta, 1 sine theta. So the difference between parameterizing for a surface and a volume, for a cylinder and this also holds for a sphere, is that when you do the volume, you're going to let the radius go from the center to the surface. When you do a parameterization for the surface, you hold the radius equal to whatever the radius of the cylinder or sphere is. Now we are ready to set up our triple integral. It's an integral over the volume. And remember, it's not over f, which is why I circled this to remind me I want to come over here to do y squared plus x squared dv. I can't tell you, sometimes when you're on an exam and you're doing your volume integral, you'll see f and you'll put it in, which you don't want to make that mistake. So I often circle it to remind myself, actually, this is what I want in my integral. So I have my x squared plus y squared dv. That's equal to, well, the z goes from -1 to 1, so that's my dz. The r goes from 0 to 1, that's my dr. And my theta goes from 0 to 2 pi, that's d theta. And then I have y squared, which is r squared sine squared theta. And I have my x squared, which is r squared cosine squared theta. I'm not sure why I swapped everything around. And then the thing you have to remember is because I didn't just use x squared plus y squared, but I converted to polar coordinates because that was what was easy to parameterize with, I need to use the Jacobian. So here's my Jacobian here. So now when you do this integral out, you'll get that's equal to pi. And what we had just calculated is the divergence of f over the volume. And again, we had a triple integral. Next, we are going to calculate the right-hand side. That'll be the surface integral of our vector field. Actually, our vector field is f, so let me just change this to f. And from our line integral formula, that's going to be the integral over the domain of f and our parameterization of our surface dotted with the normal to the surface. And if the normal isn't readily easy to see, you can use the formula Tu cross Tv, and we'll illustrate this formula. One thing about the surface of the cylinder, we're going to break it up into 3 different surfaces so we can parameterize each one easily. The first surface is kind of the body of the cylinder, what I call the body of the cylinder over here. The top portion of the cylinder is the second surface, and you want to notice this also includes the whole disk, not just the circle. You know, the circle is the boundary of the disk, because the circle is, equidistant from a center. If you want the interior of the circle over here, then we call that the disk. So it's this disk on top, and the last surface is the disk on bottom. The first surface we are going to do is S1, that's the body of our cylinder. For the surface integral, I have the steps listed here. The first thing to do is to parameterize our surface and determine its domain. So we're going to parameterize the cylinder, and as I mentioned, we're going to use cylindrical coordinates, but we don't want the interior of our circle, so we don't want the radius to go from the center all the way out. We want to set our radius equal to the radius of the cylinder, which is 1. So our parameterization is going to depend only on theta and z. And it's going to be our 1, because our radius is 1, cosine theta, 1 sine theta, and z, where theta goes between 0 and 2 pi, and z goes between -1 and 1. The next step is to write our vector field v in terms of our parameterization. So here our vector field is f. We want to write it in terms of our parameterization here. So I'm going to plug in my 1 cosine theta, which is just cosine theta, sine theta, and z into f. So plugging this in to f, and now, we're not doing the div, into f, I have x, y squared. So that's cosine sine squared. My second coordinate is x squared y. So that's going to be cosine squared sine theta. And then finally, I'm going to have y, which is just sine theta. So this is my f composed of my parameterization. The next step is to calculate my vector normal. So my vector normal is going to be Tu cross Tv, where u is our first variable in our parameterization, v is our second variable in our parameterization. So our u's and v's end up being theta and z. So first, the tangent vector with respect to theta. So here's our parameterization. With respect to theta, that's going to be negative sine theta, cosine theta, and then z with respect to theta, this is a 0, not a c. The tangent vector with respect to z is going to be 0 here, 0, and then 1. And then I cross t theta with tz, and I get my normal vector, which I'll let you do the cross product, but that will give you cosine theta, sine theta, and 0. And finally, I'm ready to set up into my formula. I have my double integral, so that is going to go, where's my parameterization? Z is going from -1 to 1, that's dz. Theta is going from 0 to 2 pi, that's d theta. And then I have my vector field composed with my parameterization, that's over here. So that's my cosine theta sine squared sine, sine theta, dotted with then my normal, which is right here, cosine theta, sine theta, and 0. If you do this integral, your final answer will be theta. And I almost wanted to say which matches here, except we haven't done surfaces 2 and 3. So either surfaces 2 and 3 cancel out, or they're both equal to 0. So let's take a look. I'm going to get rid of these notes here because I need this space. And the next surface I'm going to consider is S2. That's the top over here. I parameterize my surface, and this time, because I want the entire circle, including the interior, I'm going to let r vary between 0 and 1. And I'm parameterizing the disk. So using polar coordinates, I get r cosine theta, r sine theta. My z value is equal to 1, right? I'm at a height of z equals 1. Theta goes between 0 and 2 pi, r goes between 0 and 1, again, because I want the interior of this circle now, of the disk, and z is set equal to 1. The next steps are to compose my vector with my parameterization. So where's my vector field? xy squared, so it'll be this x, r cosine theta times r sine theta squared. So I'm going to get an r cubed cosine theta sine squared theta. I need to squeeze in a theta. What's the next coordinate? X squared y. So that will be my r squared cosine squared theta, r sine theta. So I'll get an r cubed cosine squared theta sine theta. And finally, for my last coordinate, it's just y, which is r sine theta. And then finally, I calculate my normal, which is equal to the parameterization partial derivative with respect to theta crossed with the partial derivative with respect to r, and I'll let you calculate that out and confirm that it's equal to 0, 0, r. So finally, I'm ready to set up my integral. It's my double integral because it's a surface. So r is going between 0 and 1, theta is going between 0 and 2 pi, and then I dot my n with my field composed of my parameter, but I get 0, 0, and I have an r squared sine theta. When I do this integral, I get 0. I'll let you verify that S3 is also equal to 0. So for the three surfaces, my total flux is going to be equal to pi, which is exactly what I got when I did the divergence over the volume. So again, I calculated this two ways, or I calculated both sides of Gauss's equation. First, by doing the divergence of f over the volume, and that was a triple integral because it's a volume. And then second, I did the surface integral of f, and that's a double integral because it's over the domain of our surface. Now we've done this example on our overview sheet, and since it's helpful to have more examples, more practice, we'll do a few more examples. This next example has the vector field v equals 2x y squared z squared, and S is the unit sphere, that is x squared plus y squared plus z squared equals 1. We want to use Gauss to evaluate the surface integral. And the first thing I'm going to say, when they say Gauss to evaluate the surface integral, I usually assume that they mean they want us to use this left-hand side and do the divergence over the volume. The reason why I say that is if they wanted us to do this flux through the surface, then they would say they wouldn't say use Gauss to evaluate the surface integral, they would just say calculate the flux through the surface. So they want the surface integral, but by using Gauss, they want us to use this side of the equation. That's my take on it anyway. So I'm going to use the volume integral, and I'm going to do the integral of the divergence. So my del dot v, here's my del, here's my v, which is 2x y squared z squared. So derivative, partial derivative with respect to x is 2, partial derivative with respect to y is 2y, and partial derivative with respect to z is 2z. And as I said, so later when I plug things in, I don't want to plug in z, but I want to make sure I plug in my divergence. The parameterization for a sphere, we're going to use spherical coordinates. Rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi. And as I mentioned, because, let's see, yeah, we're doing the volume integral, we're going to let rho go from 0 to 1, 0 to the radius, and this is a unit sphere, so the radius is equal to 1. We're going to let theta go between 0 and 2 pi, phi go between 0 and pi. And like when we parameterize the cylinder, because we're parameterizing the volume here, we let rho go between 0 and 1. If we were just doing the surface, we wouldn't want the interior. We'd only want the radius set equal to 1, and so we'd put a 1 here. So again, the difference between parameterizing between the volume and the surface is the volume you want the interior. So in these polar coordinate kind of spherical coordinate kind of things, you set your rho, your radius, to go from 0 to the surface of this, in this case, sphere. If you were doing the surface integral, you only want where the radius is equal to 1. You don't want the interior. Because I used spherical coordinates to parameterize my unit sphere, because that's the easiest way to parameterize a sphere, I need to change my vector field divergence also into spherical coordinates. But that's not too hard to do. But anyway, my del dot v is equal to, I factor out the 2, then I have a 1, and then I have a y, which is equal to rho sine theta sine phi, plus a z, which is rho cosine phi. And now I'm ready to set up my integral. My rho goes between 0 and 1. My theta, oh, I guess I did phi first. Oh, phi goes between 0 and pi. And theta goes between 0 and 2 pi. And then I have my divergence that I'm integrating. So that's, I pulled out my 2, my 1 rho sine theta sine phi plus cosine phi. And then I need to put in my Jacobian because I did this change of coordinates. And from there, everything else is integrating, some trig, some addition. And my answer is negative 8 pi over 3. This next example involves a cube. We're going to find the flux through a unit cube for f. I probably should have renamed this a so you don't get used to seeing f, but whatever, I guess you can figure it out. This is f equals x squared y, 2xz, z squared minus 2y. And because we're looking at Gauss's theorem, we're going to do this much like we did that cylinder example, using the left-hand formula and then using the right-hand side formula. And it looks like I started with the right-hand side where we calculated the flux over the surface. One other thing, I guess, because your book puts the du dv to make this operator all complete, I decided to do the integral that way, even though it looks strange to me. So anyway, the flux, going back and finding our formula for flux here, I have my integral over my domain du dv, our vector field composed of our parameterization of our surface, dotted with the normal, which is tu cross tv. And the thing about this surface, like the cylinder, we need to break it into 6 surfaces. And the first surface I'm going to choose is this top surface here, where z is equal to 1. So the parameterization of this surface, well, it's a square, so that's kind of nice. But anyway, so my phi of uv is equal to u and v, where u and v go between 0 and 1 because it's a square. And then also my z coordinate is equal to 1. So when I compose my f of uv1, composed with my parameterization, I'm going to get, well, I have x squared y, so that's u squared v, and then I have a 2xz, so that's 2 u times 1, just 2u, and then z squared minus 2y. So that's 1 minus 2y. So this should be minus 2v. So I've done my first two steps, parameterized my surface, wrote v in terms of my parameterization. The next thing I need to do is calculate my normal. So I take the partial derivative of my parameterization with respect to my first variable, and that's u. So that's going to be 1, 0, 0. Then I take the partial derivative with respect to v. So partial derivative of u with respect to v, well, that's just 0. I have 1 and I have 0. Then I take the cross product of tu cross tv, and that will give me my normal, and I see it's equal to 0, 0, 1. And actually, that's not surprising. This shape here, this plane, those are pretty easy to get normals for, right? The normal for the plane is, either straight up or straight down, but because we're talking about a volume, remember the positive orientation is pointing away from the interior of the box. So it's straight up, which is exactly what we got when we did this cross product. But for the other surfaces, we're probably not going to do it. We're just going to figure out what the normal is. And now I'm ready to plug into my formula. I have my double integral. Both u and v go from 0 to 1. And then I have my function composed of my parameterization. That's u squared v tu, 2u, 1 minus 2v. And I dot it with my normal, 0, 0, 1. So I have 0 plus 1 minus 2v. I take the integral with respect to u first. So I still have my dv. With respect to u, I guess I would add a factor of u, integrate between 0 and 1, I get 1. So I'm left with 0 to 1 dv, 1 minus 2v. When I integrate this with respect to v, I get v minus v squared evaluated at 0 and 1, and that will give me 0, because I have 1 minus 1 is 0. For my second surface, I'm going to do this front face here along the x equals 1 line. So here I have my surface, just a reminder that x equals 1. So when I parameterize my surface, in this case now, y is going between 0 and 1, and z also goes between 0 and 1. So I get my phi of uv, x is set at 1, y and z both go between 0 and 1. So that's u and v between 0 and 1. So when I do my function composition, so I take this, I have x squared times y. So that's x squared is just 1 times y, so I get a u for the first coordinate. Then I have 2xz, so 2 times x is 2 times z, which is v, so 2v. And then finally, z squared minus 2y. So z squared is, where's z squared? This should be v squared minus 2y minus 2u. I have this reversed. And I dot it with my normal. But for this surface, again, as I said, we're just going to take a look at it and see what the normal is. But the normal, if it's pointing out away from the interior of this cube, is going to be in the positive x direction. So it's going to be 1, 0, 0. And now I'm ready to plug in my formula. I get my double integral. U and v go between 0 and 1, du dv. I have my f composed of my parameterization, which is u 2v, u squared minus 2v, dotted with my normal 1, 0, 0. When I do the integration, I get 1/2. To save us some time, I'm not going to do all 6 surfaces. I do have the calculations for the third surface here. That's this one here at y equals 0. Also note the norm means I'm going to be pointing in the negative y direction. And I'll let you do the other 3 surfaces, but once you have done all 6 sides of the cube, you can sum up all the fluxes and you should get 3/2. And now we're going to do the same calculation, the flux to the cube, using the other side of the Gauss theorem, which is the volume integral. But thankfully, it's much faster than the surface integral because we're not doing 6 little tiny problems. We're going to do 1 problem. So we're going to compute the divergence over the volume, and we'll show that that's equal to the flux. And the first thing we do is we convert the divergence. This is del cross our field x squared y to xz, z squared minus 2y. Partial derivative with respect to x is 2xy. Partial derivative with respect to y is 0. Partial derivative with respect to z is 2z. And now also, again, so I don't plug in the wrong thing, I don't want to be integrating f, I want to integrate the divergence. And now we can set up our integral. It's a cube, which is so nice. It's so easy to integrate. But we have x goes between 0, 1, y goes between 0 and 1, and z goes between 0, 1. And this is what we're integrating, 2xy plus 2z. Remember, we're integrating the divergence. And from there, it's, the integration, the calculations, and we get our final answer of 3/2, which would have been exactly the same thing we had done when we calculated the flux through the surface. If we had done all 6 surfaces, we would have gotten 3/2. You'll just have to take my word for it, or you can check it out, calculate it yourself. The other 3 surfaces, add them up, and that's equal to the divergence through the volume. I have one more example to do, and this one I promise is worth your time, and it's short. In fact, this page is the whole thing. So we want to find the flux of this vector field V, which is equal to e to the y cosine z, x cubed plus 1 square rooted, and x squared plus y squared plus 3 over the surface z equals to 1 minus x squared minus y squared times e raised to the 1 minus x squared minus y squared, and this surface is for z greater than or equal to 0. And we are going to use Gauss's law, and the reason is if I had to calculate the flux and then I had to parameterize this surface on an exam, I would be utterly panicked because I don't even know where to start. So out of sheer desperation, I think, okay, maybe I could use Gauss's law. So I'm going to consider the divergence over the volume. Again, just out of sheer panic because I don't know how to parameterize this. So to start with Gauss's law, I need to take the divergence of the vector field. So I'm going to take the divergence of this vector field V. So that's the del dotted with e to the y cosine z, square root of x cubed plus 1, x squared plus y squared plus 3. So the partial derivative of this first term with respect to x is 0. The partial derivative of the second term with respect to y is 0. And the partial derivative with respect to z of the last term is 0. Therefore, this side of the integral is equal to 0, meaning the flux over here is also equal to 0. So Gauss's theorem is not always about doing the integral 2 ways, and in fact, it's definitely not that. 1, it tells you something about a physical thing, and then 2, sometimes one side is easier to do than the other. To review what we have discussed in this video, we talked about Gauss's theorem, which is written here, and it relates divergence over a volume to the flux through a surface. So on this left-hand side, we have a triple integral. It's a volume integral of the divergence of a field A, and related that to the flux, which is a surface integral of that same vector field A, where this surface here is the boundary of this volume on the left-hand side. We reviewed the surface integral operator on a vector field, since that is the right-hand side of Gauss's equation. And we also reviewed, and I say reviewed, I don't think we talked about it in this class, but we reviewed it from vector calculus, the Jacobian. I gave you a formula, the determinant formula to calculate the Jacobian, but I also told you that for polar and cylindrical coordinates, the Jacobian is r, and for spherical, I find this more convenient to memorize than to calculate, is rho squared sine theta. And we use this Jacobian whenever we do a change of coordinate systems. And that often happens, like in this example here, we're talking about the surface is a cylinder, which is easy to use cylindrical coordinates to parameterize. However, our vector field is not given to us in cylindrical coordinates, so we have to change it over. We have to transform it, and when we do that, we need the Jacobian in our integral. And finally, we did a number of examples, such as this one here, where we had a vector field and we had a surface of a cylinder, and we calculated both the divergence over the volume, which is this calculation here, and then we calculated the flux through the surface, which was this calculation here. And I'll spare you from having to review those calculations, but it's here. And we did a number other examples in just as much painful detail where we did both sides of the equation, And then we did some other quicker examples as well. So that's it for this video. Thank you for watching.